jets. My name is Chongqing from the School of Aerospace Engineering in Beijing Institute of Technology. I'm going to split this presentation into 5 parts. Research background will be the first part, then it will be numerical methods, experimental validations, results and discussion, and finally the conclusion. So our research focuses on the impinging jet due to their high atomization efficiency, which makes them suitable for liquid rocket engines. This shows a schematic diagram of a duplet impinging jet. Impinging jet injectors utilize the impact of liquid jets to transform the liquid from jets to a sheet. The instabilities in the liquid sheet then disintegrate the sheet into discrete droplets. The most straightforward and frequent configuration is the collision of 2 identical liquid jets at an acute angle, commonly referred to as a duplet. The advent of a large-scale space operation such as human space flight and deep space exploration has increased the demand for liquid-fueled carrier rockets. This study will help us to understand the effects of backpressure, variation on jet atomization mechanism, and spray patterns, which is beneficial for enhancement of the performance and reliability of liquid rocket engines. Due to the high complexity of the numerical method, the use of a supercomputer is needed to provide more accurate and reliable DNS simulations. Multi-phase flow field obtained from our simulation have enough details to understand some of the fundamental processes governing turbulent motions, specifically how droplets form, coalesce, and break up, or the surface tension dynamic between liquid and gases for capturing a large enough area to see how these motions impact jet streams. Droplets are formed and influenced by turbulent motions, but also further influence turbulent motions after forming, creating the need for very detailed and accurate numerical simulation. In our studies, we use inter-isoform in OpenFOAM. Inter-isoform is a solver for 2 incompressible isothermal miscible fluid with optional mesh motion and mesh topology change, including adaptive remeshing using iso and vector phase fraction based interface capturing. The basic method used are the volume of fluid, adaptive mesh refinement, load balancing, interface reconstruct. The governing equation used in this study is Navier-Stokes equation for incompressible flow. We use iso and vector method where we have compared the differences between multi-cut piecewise linear interface calculation method, also known as the MPLIC method, and the iso and vector method, and found out that iso and vector method shows a more realistic surface disturbance. It uses a series of geometric planes known as isophase to reconstruct each interface grid based on current volume fraction field. Furthermore, iso and vector is a geometric volume of fluid method for advection of a shut interface between 2 incompressible fluids, working on both structured and unstructured meshes with no requirements on the cell shape. Here we have an overall structure showing a boundary condition. At the outlet of the tank, we have designed a slight cut to the inlet of the nozzle to have a realistic numerical model. The acute angle of the jet is at 60 degrees, where the orifice has a diameter of 0.3 mm. Snappy hex mesh is used to create a mesh for the model. We have also used local mesh refinement at the orifice. In this slide, we can see that the adaptive mesh refinement is used. We have added a more refined mesh at the orifice to get a better understanding of the flow. We can see that it captured the development of turbulent flow in the nozzle. This provides us a more in-depth understanding to the turbulence occurring in the nozzle. By using the numerical model, we can split it into 5 different cases, each having the same liquid, diameter, acute angle of jets, and the velocity, whereas the back pressure is modified from 0.1, 0.5, 1, 2, and 4 megapascal. Sugon computing service is used in all of our simulation. We then make a study on the independent grid with 4 megapascal and split the grids into 3 different resolutions, which is low, medium, and high, each having 15, 30, and 60. The adaptive mesh number billion cells. Furthermore, the equivalent to uniform mesh is 54 million for low, 432 million for medium, and 3.45 billion cells for the highest resolution. In this graph, we have compared the solder mean diameter and the spreading angle grid resolution. We found out that the 30 and 60 grid resolution does not have a major difference. Because of that, we have made two models of different resolutions. Model 1 shows a high resolution where we can get better understanding of the atomization dynamics. Model 2 shows a medium resolution, which shows a longer computational domain spread dynamic. Numerical simulation of jet surface perturbation was successfully achieved where the simulation matched well with the experimental observation by using the interface reconstruction algorithm. The iso-effector method. The perturbation of the jet surface influences the interfacial interaction, which results in the formation of liquid film disturbance. This figure shows the comparison of experimental and numerical results of both 0.1 and 4 megapascal at high resolution. Here we can see a side-by-side comparison of experimental and numerical results under 0.1 megapascal at medium resolution. Whereas this is the comparison of experimental and numerical results under 4 megapascal at high resolution. From the chart above, we can note that the validation of solder mean diameter and the nozzle spray angle. Our study shows that the numerical simulation results are close to similar as per our experimental results, suggesting that our simulation results are accurate. The measurement method used for SMT is phase Doppler particle analyzer, and the spreading angle is measured using flow field from particle imaging velocimetry. During our simulation, we found out that as we increase our back pressure, the jet surface becomes sharper, showing a transition from a rounded convex structure to a scale-like structure. We can see from our front view, as the impinging jet interacts, the formed liquid sheet gradually decreases in size, resulting in reduced surface fluctuations and a decrease in the length of sheet breakup. After the breakup of the liquid sheet, the formed liquid ligaments gradually transform into liquid pockets. This is the side view of the impinging jet interaction from 0.1 megapascal to 4 megapascal. It is shown that with the increase of back pressure, the development of the spray field changes from dilute to dense, indicating that there is an overlay of water droplets. Furthermore, we studied the distribution of vorticity field and found out that the intensity of vortices in the liquid phase is significantly lower than in the gas phase. Whereas in the liquid phase, vortices with higher intensity are shown in the impinging point of the jet. During the gas phase, vortices with higher intensities are shown on the surfaces of the liquid fluid. In these diagrams, we can observe that the counter-rotating vortex pairs can wrinkle and pinch off liquid structures. However, separated liquid structures can induce vortex pairs in a similar manner. Furthermore, we can observe that as the back pressure increases, the intensity of vortices around the liquid sheet and droplets noticeably decreases. However, the number of vortices significantly increases, especially in the region of liquid sheet breakup. By using the Q criteria, we calculated the iso surface. The image shows the 3D image of the vorticity structure distribution. As the back pressure increases, more small-scale vortical structures appears on the jet and liquid sheet surface. However, the size of vortical structures on the liquid sheet surface noticeably decreases. Vortical structures are almost absent on the surface of the droplets. We also studied the topological structure. The series divides the flow field into 4 structural parts, S1 being the unstable focus / compressing, S2 being unstable node / saddle, S3 being stable node / saddle, and S4 being stable focus / stretching. The topological field verifies the impression of the vorticity field. As the flow structures in the region of the liquid sheet breakup become smaller and more densely distributed with increasing back pressure, the different back pressure condition The internal topological structures of the jet are similar, with the dominant features being S2 node in the region of the jet impinging. To better understand the topological structures volume distribution of both liquid and gas phase at different pressure, we have made a graph with integrate cross-section lines showing the different topologies. This shows the topological structure volume distribution of liquid and gas phase at 1 megapascal and 2 megapascal. During liquid phase, as the back pressure varies, the share of different topological structures in the jet region remain relatively constant. However, as the flow passes through the liquid sheet region, the proportion of S2 structure sharply increases. In the droplet region, with the increase of back pressure, the proportion of S1 and S4 structure gradually increases, while the proportion of S2 and S3 structures gradually decreases. During gas phase, as the back pressure changes, there is a significant change in the share of different topological structures in the jet region and droplet region. So while there is a decreasing trend in the proportion of S2 and S3 structures, there is an increasing trend in the proportion of S1 and S4 structures. As we see from the grid resolution of 30, the SMD value shows that it is decreasing from 103.4 until 95.2, and then it increases up to 112.7 as the back pressure increases. We can also look at the grid resolution of 60, where it decreases from 100.1 until 96.4, then it gradually increases until 115.2. We calculated the differences between the two grid resolution, and the difference is negligible. By doing this, we discovered that we can use grid resolution of 30 for our future simulation to save the processing of time. This page shows that we can use medium resolution to measure the near field and the far field at all different back pressures. This video represents the result of the back pressure at 0.5 megapascal with a downstream distance of 30 mm. And this video represents the results of back pressure at 2 megapascal with a downstream distance of 30 mm. Overall, there is a shared trade where the SMD will increase until a platform, where then it stabilizes. 0.5 megapascal shows a very good agreement with our experimental results. Both of these shows a very good agreement with our experimental results. When the back pressure is at 4 megapascal, there is a serious build-up of droplet, resulting in a large deviation between experimental values and numerical simulation results. Liquid filaments or clusters formed by liquid film breakage continue to break as they travel downstream, leading to a decrease in liquid surface area and an increasing average droplet diameter. As the downstream distance increases, the droplets will collide with each other and coalesce, leading to an increase of an average droplet diameter. We also devised a method to develop spatial distribution of SMD based on the spreading angle. We obtain a fan-shaped region, then divide the fine-shaped region into a few fan-shaped angles at different angles. This graph shows a preliminary results of the SMD of each area where it fluctuates over time at a certain range, where we can observe that the SMD peaks in the middle region, resembling a quadratic equation. In conclusion, direct numerical simulation is performed on the impinging jet atomization using the into-isoform solver from OpenFOAM. The simulation incorporated the real nozzle structures to accurately capture the atomization process. It shows there is a good agreement with the simulation and the experimental result, verifying the method. A high-resolution simulation was employed to investigate the atomization process of the impinging jet atomization in the near field. The simulation reviewed the atomization process and provided a detailed analysis of the vortices and flow topology in the atomization field. Simulation on the far field of the impinging jet atomization was conducted using medium resolution. The simulation analyzed the variation of droplet diameter with downstream distance providing insights into the behaviors of droplet as they travel further downstream. Thank you.
Okay, thank you. I have a question about the droplet collision. I want to ask you, how do you deal with the droplet collision during the impinging jets? As we all know that the droplet collision will rebound, merging with satellite and different reverse. And as well know that the interface captures is very important for the gas and liquid flow. So how do you deal with that? The droplet collision.
I'm sorry, I didn't get it.
Okay. My question is, how do you deal with the droplet collisions in your liquid?
Droplet collision as in...
Yes.
So actually during our simulation we found out that actually droplets, they collide and actually we see their diameter getting bigger, increase in diameter. So from there we can actually see that the difference between before and after they collide.
Okay, so given the timings, we have to move on the next talk. Thank you again, I'll speak.
Right, thank you.